You may well have used the pprof tool to profile the amount of memory your program is using, but it can also be used to profile the amount of CPU to find out which are the slowest parts and what you should be going about optimizing. Use it with the runtime pprof package, and there are a couple of functions to start CPU profiling and then stop it and save out a file for use with pprof. To illustrate how this works, I've implemented an LRU, least recently used cache, rather badly in Go, and I'm going to use it and use the profiler to actually figure out why it's slow, why I'm a bad programmer in this case. So let's just take a look at the package. This is the LRU package here, and the idea is it creates some sort of cache of items. It has a certain size, this capacity, that's the number of items it can store. And the implementation is a map, mapping strings to things, and those things are keys, the values that are stored along with them, and the last time they were accessed. And we need the last time to do the LRU thing. Once it reaches capacity, we need to start evicting things. When you put something in the cache, if it's full, if it's at capacity, then you have to make space, and whatever happens, you insert something into the cache. When you retrieve something, that's fairly simple. You just look up the item in the cache, set the time to now because it's been used, so you want to bump it up to be something that shouldn't be evicted, and then return the actual item, and if it's not there, it's nil. And the making space function here, what it does is it iterates through the things that are in the cache, looks for the oldest item to remove, and then we'll actually remove it. So this is what it does here. It goes through, it says, are you older than the oldest thing I've seen? If so, then you'll keep that key around, and eventually we'll delete it using the delete keyword from the map. So fairly simple LRU implementation, and I've got a small program, and what it does is it reads in something on standard in, actually words, and chops off the first letter of each word and just takes the next 3 letters. So I'm just generating some data here so that the cache gets exercised. And I'm actually going to feed it the entirety of War and Peace word by word. And we're going to take all those words and cache them. And I've set the cache size to be up to a maximum of 1,000 of these word fragments. And I'll store the last word I saw with that particular fragment in it. This could be any realistic data you're using in LRU cache. This is just some handy textual data that I have lying around. So, in order to profile this, I'm going to use pprof here, and I'm going to output a file called lrutest.cpu profile. I'm going to start profiling as soon as the program begins, and when it terminates, stop it, which will write the file out before it terminates. So this will give me a complete view of what happened inside the cache. So let's just make sure this builds. And that's great. And I've got War and Peace here, which I think is, there you go, over 500,000 words. So we can feed that in. And I'll just take that and feed it into LRU test. And so it's going to be going through, filling up this cache with a maximum of 1,000 items. And so there it's run. So you can see that, there were 24,000 misses, so 24,000 times when the thing wasn't already in cache, and so we had to obviously go ahead and evict something. And I can then use the profiler to look at the performance of that. Now in this case, there's not very many misses for the total number of items, and so it's probably the case that it's not that interesting. I'm going to try, there's another thing I can use, which is the dictionary. And I can pipe that in. And now I've got a large number of misses here. So either of these I think will be good techniques we can use, files we can use to look at it. So let's look at the profile file. It should be here. There it is. And I can feed that into the pprof tool like this. So we're just saying this pprof tool on the program, here's the CPU profile. And I can take a look at where the time went. And what we find is very quickly that these two things are at the top here. If you notice, 75% of the time being spent in this. Runtime map iter next is iterating a map. So somewhere in my code there's a map iteration that's happening, and in fact you can kind of see that make space, whatever that function was, that was where it seems to be happening. Now, it looks like it's in LRU1, so I can do a couple of things. One is I can use list, and I can go in, I can just list out here, and I'm going to see that, here's that call, you see 200 milliseconds on that call to make space, and of that 190 milliseconds here. So this is where the problem is. It's the iteration of the C data, which, if you recall, is the map which we're using to store the cache in with the times. And this is what happens is when you try and evict something, it's going to run through this make space function and has to iterate everything. So you can imagine it's iterating over that map, which is a bit silly. And that's where the time has gone. Another way to view this, of course, would be the web view. So if I go in and do web, and I'm going to get a view like this, and you can quickly see that here's the main program. It takes 220 milliseconds to run. And of that 220 milliseconds, 200 milliseconds, almost all of it, was in the put function, so adding something to the cache. And of that, almost all of it was in make space, and almost all of that was in that map iteration. So quite clearly, this is the branch that we need to optimize to make this LRU cache more efficient. And so what I'm going to do is I'm going to go ahead and do that, and we'll look at the effect this has. So obviously iterating a map like that every time you wanted to insert something into the cache when it was full was a bad idea, because it would create 1,000 iterations, or depending on the map size, it could have been even larger. What we need is a different kind of data structure, and what I've done here is I've changed the way things are working to use a list, and then using a list move to front operation to keep the least recently used element. So the idea is I've got rid of time completely, and within my cache structure now, I've got data, right here it is, that's the map I had before, but it's pointing to a list element, which is something that comes from container list. And I've also got a list pointing to the same elements. So I'm keeping two places pointing to the same data. And so now when I get something, what I do is I move the item that we're getting to the front of the list. We find it by looking in the map, so we find the list element, and then we say to the list, okay, move that to the front. That's where we get the least recently used from. And then we return the actual item that's in there. This is the syntax for doing that. So although the list contains an interface, an empty interface, we use this type assertion here to say it actually contains a pointer to an item. When you're putting something, if we're at capacity, then we just delete whatever is at the back. So the thing at the back will be the least recently used on the list, and we remove it from the actual list of data. And then we push on the new thing on the front, because that's obviously the most recently used. So this is a much more efficient way of doing this, because it doesn't require any iteration, although there are two different data structures. There's no change to the original program, so let's go build that. And let's just put through the same thing again. Okay, there we go. And it seemed like it was a bit snappier. And we'll have the same profile there, so let's run the profile tool. And now we've got a totally different view of things. Now, all the time that's being spent, first of all, it only took 10 milliseconds, not hundreds, and all of the time is being spent doing this thing, syscalling here. So let's just bring up the web view. It's got a hell of a lot simpler now. And you can see that, in fact, all of the time is being spent actually reading the file. So if I was going to spend any time on this, it would be bulk reading perhaps, and then doing the splitting of lines myself. But right now, this program is pretty fast compared to where it was before. And you can continue down this. We could then start looking at different operations in here of your program to try and optimize it even further. But for this LRU cache, I think it's pretty efficient for what it is for the moment.